The topic of this video is spectrum and Fourier analysis. However, we will not be going into the mathematical details of this topic, but we'll try to understand what is a spectrum and what is Fourier analysis without going into too much details of the mathematics behind it. The math we'll discuss at some point later in a later video, but the focus of this video is to understand what a spectrum means and what is Fourier analysis and how do we obtain the spectrum of any signal. Right. First of all, if you notice these two waveforms here, they are both in the time domain. So what we have on the x-axis is time. So both these are in the time domain. So basically these waveforms or signals are nothing but voltages changing with time. So we call them to be existing or present in the time domain now as time domain signals. In contrast, the spectrum is a representation of the same signals but in the frequency domain. So we will transform the signal from the time domain to the frequency domain. So that means the spectral representation would be a plot or a graph which has frequency f on the x-axis and some other parameter on the y-axis. Now, why is spectrum important? Because it gives us a perspective into the signal from in a different way in terms of the frequency content present in the signal. The first thing we need to remember here is that how do we convert a time domain signal to frequency domain signal. So the transformation or the mathematical procedures that are performed to convert from time domain to frequency domain is the Fourier transform. So that's the transformation that is used to go from time domain to frequency domain. There are variations of the Fourier transform which are referred to as the Fourier series and the discrete Fourier transform, the DTFT, the discrete time Fourier transform, and so on, depending on the nature of the signal in the time domain. Again, we'll leave these topics for another session, but they simply represent all these transformations as the Fourier transform. They mean the same thing, just the signal in the time domain is of a different nature. Right? So we have three definitions here. First is the time domain representation of the signal. Then we have the spectrum, which is the frequency domain representation of the signal. So we have this as the spectrum, which is the frequency domain representation of the signal. And how do we go from time domain to frequency domain? By performing what is called as the Fourier transform. Now, broadly, what the spectrum, what information does the spectrum give us? The spectrum tells us about the frequency content of the signal. So spectrum is nothing but frequency content of the signal. So this is the information we get from the spectral representation of a signal. Well, if you look at these two waveforms which are here, these are very simple waveforms which contain only one frequency. So we can directly see from the signal itself what is the frequency of the signal. For example, this particular signal is a cosine wave which completes one cycle in 1 second. That means the frequency of the signal is 1 Hertz. Similarly, this waveform is completing two cycles in 1 second. So that's the time unit of 1 second, and from 0 to 1 second it has undergone or completed 2 cycles. So that means this particular signal here is having a frequency of 2 Hertz. So The spectrum will give us the frequency content of these signals. So it will have frequency on the x-axis and the magnitude of the signal on the of that particular frequency on the y-axis. So it gives us the frequency content. But the frequency content itself can be of two types. We can have the magnitude of that particular frequency, but it can also have a representation of the phase at that particular frequency. So the spectrum is of two types, or it contains two pieces of information. So that is, we can have the first type, which is the magnitude spectrum, and then we have what is called as the phase spectrum. So that means the magnitude spectrum gives us information regarding the magnitude of the different frequency components present in the signal, and the phase spectrum gives us information related to the phase of those frequency components present in the signal. Now the focus of this video will be restricted to magnitude spectrum, again without going into the mathematical details of it. We'll come to a more detailed discussion, including the detailed mathematical notations and representations, in another separate video. Okay, right, now let's try to understand the spectrum of these two waveforms which we have here. So we'll try to plot the spectrum of these two waveforms. So let's go here. As we discussed, this particular waveform is completing one cycle in 1 second. That means the frequency of this signal is 1 Hertz, and it is only that one particular frequency. So the frequency of this signal is f equals 1 Hertz, and similarly the frequency of this signal, which is x2 of t, we just name it as x2 of t, and this one as x1 of t. So x2 of t is completing 2 cycles in 1 second, so that corresponds to having a frequency f equals 2 Hertz. And as we said, the spectrum, or the magnitude spectrum, gives us the frequency content or the magnitude of the different frequencies present in the signal. Now one of the things that we also need to do is the notation is that if we have a signal in the time domain denoted by, say, x of t, or x1 of t, then we denote the corresponding spectrum as x1 of f, since frequency is the independent variable, and since we are interested in the magnitude, we'll call it represent as the magnitude, like that. And it is also possible to go from the frequency domain back to the time domain. So the transformation that is done to go from the time domain x1 of t to the frequency domain x1 of f is the Fourier transform. So we'll simply write the Fourier transform as ft, and the inverse operation is also possible. So we can go back from the frequency domain to the time domain by performing what is called as the inverse Fourier transform. Again, the mathematics, will deal with that in a separate lecture or separate video. Okay, coming back to these representations of the spectrum. So we are doing what is the magnitude spectrum. So these are nothing but magnitude spectra of these signals, since we have frequency on the x-axis and the magnitude of those signals on the y-axis. Now the first signal x1 of t is having a frequency of 1 Hertz. So on the frequency axis we will have this notation, this signal present at a frequency of 1 Hertz. So this frequency, if we say this is in Hertz, so it exists at 1. And what is the amplitude of that particular frequency? If you notice here, the amplitude is 1, 2, 3, 4. So it's going up to 4 volt in amplitude. So the amplitude should be represented as 4 volt present at 1 hertz. But the convention that we will do is whatever is present at 1 hertz we will place a mirror image or a replica of that at a negative frequency of the same value, minus 1 hertz, but we will divide that particular magnitude half and half between the positive and the negative components. So we will remove this 4, and in place of the 4 we are going to make it 50% of the 4, which is 2. So we'll make it half of it on the positive frequency and half of it on the negative frequency. So that means at 1 hertz we have a magnitude of 2 volts, and at minus 1 hertz we have a magnitude of 2 volt as well. Now why do we have this negative component, the negative frequency component, and where does it arise from? That arises from the math, and it is just a mathematical convenience. The negative frequency, as you would see in one of my earlier videos, negative frequencies do not exist in the real world. They are present in our analysis only for as a result of mathematical convenience. So this is the convention that we will follow. Whatever is the frequency present, we will have that frequency represented, but the magnitude we will divide half of it on the positive frequency and the remaining half on the negative frequency. So since the magnitude here is 4 volt, we give half of it, that is 2 volt, to the positive frequency component, and another 2 volt, the remaining half, to the negative frequency component. Similarly, for the second signal x2 of t, whose frequency is 2 hertz, now the spectrum will therefore be having a notation or an impulse present at 2 hertz and a corresponding replica at minus 2 hertz. And what is the amplitude of each of these 4 components? Since the amplitude of this particular signal is also 4 volt, and we have to divide that half and half between the positive and the negative frequency components, so we'll have to put 2 volt on the positive side, so that's 2 on the positive and 2 on the negative frequency components. So that is basically what is called as the magnitude spectrum. So if we look at only these spectral representations over here, these give us information about the signals on the left, but on the frequency domain it tells us what is the frequency present in the signal and how much is the magnitude of that particular frequency. So similarly here it tells us that there is a frequency of 2 hertz present and it has a magnitude of 2 volt, and minus 2 hertz present and has a magnitude of 2 volt, or basically it's there is a signal present at 2 hertz having a magnitude of 2 plus 2, that is 4 volt. Right, let's take this a bit further to a signal which is not so, whose frequency content is not so apparent as in this case. Okay, these signals we can clearly see what is the frequency present because these are sinusoidal waveforms and their frequency can be determined based on their time periods directly. But not all signals that we encounter in practice are so apparent in terms of their frequency content. So let's look at one more example where it may not be so apparent. So if you look at the first signal here, and if we can call this as, say, x1 of t, and the red signal, if we can call this as x2 of t, and the third signal that we have here, this last one here, is basically a summation of x1 of t and x2 of t. So I have produced this third signal here by adding these two waveforms together. So x3 of t is basically x3 of t is basically, or it has been produced by adding x1 of t and x2 of t. Now if we look at the waveform for x1 of t, it is apparent what its frequency is. For example, it is completing one cycle in 1 second, so this is a frequency of 1 hertz. So if we write this is frequency equals 1 hertz. Similarly, if we look at the red waveform, which is x2 of t, it is completing its 1 and 2 cycles in 1 second, so that corresponds to a frequency of 2 hertz. So f is equal to 2 hertz. But if we look at the third waveform, it completes one cycle from here to here also in 1 second, but it doesn't tell you what all frequencies are present in the signal. So you can't readily find out that this signal contains a 1 hertz component and a 2 hertz component, because as I said, I have produced this particular waveform by adding x1 of t, which is having a frequency of 1 hertz, and x2 of t, which is having a frequency of 2 hertz. But if I did not show you the blue waveform and the red waveform and showed you only this black waveform x3 of t, then it wouldn't be apparent to look at this waveform and say that this waveform contains a component at 1 hertz and another component at 2 hertz. So in order to find that information, we'll have to take the Fourier transform of this particular signal, and the Fourier transform would then give us information related to its frequency content, and hence we can get that information from the spectrum of x3 of t. Excuse me. So simply put, if we had to plot the spectrum for x1 of t, let me just draw it very roughly, just to be complete here. So if we had to draw the magnitude spectrum for x1 of t, we'll simply call it as x1 of f and its magnitude. So since it's 1 hertz, so it will have an impulse at 1 hertz and an impulse at minus 1 hertz. So it's 1 and minus 1. And since the amplitude of this is 1 volt, that means it is that 1 volt would be divided half and half between the positive and negative components. So we'll have it as 0.5 over here and 0.5 over here. Similarly, for x2 of t, if we had to plot the spectrum, let me draw that a bit neater. So x2 of t, we'll have frequency on the x-axis, and we'll call this as x2 of f magnitude, and it is having a frequency of 2 hertz. So 2 hertz would be further away than 1, so we'll have it at 2 and minus 2. And again, the amplitude, since the amplitude of the 2 hertz signal is also 1 volt, it is half positive and half negative. Half of it would be on the positive frequency, that is 0.5, and half of it on the negative frequency, 0.5. Now, since we know from that the x3 of t has been produced by adding x1 of t and x2 of t, that is by adding the 1 hertz signal and the 2 hertz signal, naturally, if we had to draw or plot the spectrum of x3 of t, spectrum of x3 of t, then we'll have to plot it something like this. So we'll have frequency on the x-axis and the magnitude on the y-axis, x3 of f, right? And what are the frequencies present in x3 of t? Since we have added x1 and x2, which is of 1 and 2 hertz respectively, x3 of t has a 1 hertz component and a 2 hertz component. So that means x3 of f will have a component at 1 hertz and a corresponding replica at minus 1 hertz. Similarly, it will have a component at 2 hertz, so at 1 and minus 1, and we also have a component at 2 hertz, that's 2 and minus 2. So we'll have 2 and minus 2. Right, in this particular example, since I have taken the amplitudes of both x1 and x2 to be the same, we have these representations of the same height for both 1 Hz and 2 Hz. But it is quite possible that signals have different magnitudes for different frequency components. So x1 of t, the 1 Hz component is having an amplitude of 1 volt. So we divide it half and half between the positive and negative frequency. So it's 0.5 here. So that means this height here is 0.5. 0.5. And similarly at the 2 Hz component, it's half positive. So it's 0.5 and so 0.5 and so on. So that is the spectrum of x3 of t, which is x3 of f. Now if you notice here, when we have plotted this the magnitude spectrum, so this is the magnitude spectrum. So let me be more precise. Magnitude spectrum of x3 of t. Now the magnitude spectrum of x2 of t as well as x3 of t has some missing information. For example, in x1 of t, we know it's a cosine wave. It's a cosine wave of frequency 1 Hz. So we put a component at 1 Hz on the spectrum. The signal for x2 of t, we know that it is a frequency of 2 Hz. So we put a component at 2 Hz. But what is not apparent from the spectrum here is that x1 of t is a cosine wave, but x2 of t is a sine wave. So this magnitude spectrum tells us that there is a component at 2 Hz, but it doesn't tell us that this component is sine or cosine. Generally, the notation is that we represent the spectrum completely in terms of the cosine wave. Okay, again, why the cosine wave is our reference? That arises from the mathematical representation, and we'll leave that for later. But let's focus simply on understanding that, and just remember that we represent the spectrum only for the cosine components. So it automatically means that this is a cosine component at frequency 1 Hz having a magnitude of 0.5 volt. Similarly, it also means this means that there is a cosine component of frequency 2 Hz and magnitude 0.5 volt. But in reality, this is not a cosine but a sine. So we have to provide that missing information that this is not the cosine but a sine, and that missing information has to be provided by, or it is provided by, the phase spectrum. So the magnitude spectrum gives only part of the information in the frequency domain about the signal. The rest of the information is contained in the phase spectrum. So basically the sine wave can be represented as a 90 degrees shifted version of the cosine wave. So we just say this is a cosine wave of frequency 2 Hz but with a 90 degrees phase shift. So the phase spectrum will give us that information related to the phase shift. So similarly here, this is x3 of t is the sum of a cosine wave of frequency 1 Hz and a sine wave of frequency 2 Hz. But the magnitude spectrum does not give us the information related to to this being sine or cosine. We just interpret this as being a cosine. So we'll have to add the missing information, we have to provide the missing information by depicting the phase spectrum, in which we will show that this is a cosine wave with a 0 phase shift, and this is a cosine wave with a 90 degrees phase shift. So a cosine wave with a 90 degrees or minus 90 degrees phase shift is a sine wave. So the complete information in the frequency domain is provided by magnitude and phase spectrum together. So to get the complete information in frequency domain, we need two pieces of or two parts of the spectrum. One is the magnitude spectrum, and the second one is the phase spectrum. We'll be doing some examples related to that in a separate video. So together, the magnitude and phase spectrum give us the complete representation about the frequency content present in the signal. Right. The next thing we want to do is we want to notice a few things about these spectral diagrams that we have made up to now. So if you look at these spectral diagrams, we notice that these spectral diagrams are discrete in nature. They are not continuous but discrete. They exist, they contain components only at specific frequency components. In between, there's nothing present there. So basically the spectrum is the spectra that we have drawn here, this one as well as this one as well as this one, they're all discrete. Now if you look at the time domain waveforms for these corresponding spectra, we notice that these time domain waveforms are periodic in nature. So one of the observations we draw from this is that if the time domain signal is periodic, then the spectrum or the Fourier domain is discrete in nature. So periodic in the time domain corresponds to discrete in the frequency domain. So let's note down this point. So we can have time domain and frequency domain. Time domain and frequency domain. So since sine and cosine and sum of sine and cosine are all periodic, so when we add sines and cosines, we end up with a signal which is still periodic. So if we have a signal which is periodic in the time domain, then the frequency domain or the spectrum is going to be discrete. And the opposite would also be true. If we have something discrete in the time domain, then we are going to have the frequency domain or the spectrum to be periodic. Right? This is an important observation, and again we'll use this information at some point later in a future video, but it is an important observation and a property that if the time domain waveform is periodic, then its corresponding if the time domain waveform is periodic, then this spectral representation is discrete. If similarly here the time domain is periodic, the spectral representation is discrete, and conversely, if the time domain is discrete, then its spectrum or the Fourier transform would be periodic in nature. Okay, now let's go into the mathematical notation of the spectrum. So let's go into the mathematical notation only without going into the process of doing the actual computation. So just by looking at those diagrams from the previous pages, also from these diagrams here, so just by looking at these diagrams, we'll try to write these representations mathematically without actually going through the mathematical process of computing the Fourier transform. So mathematical notation of spectrum. Mathematical notation of. So let's take the first example of frequency 1 Hz, where we had x1 of f. It had a component at 1 Hz and minus 1 Hz. So that's 1 and minus 1 with an amplitude of 0.5 and 0.5. So if we had to write write an expression for x1 of f, so x1 of f would simply be what is this particular signal here? It's an impulse function which is present at f equal to 1. So it is basically delta, it's a delta function, delta of f, but this delta of f is shifted to the right by 1, so it's f minus 1, and this delta function has an amplitude of 0.5, so we'll write it as 0.5 delta of f minus 1, and we also have a corresponding component at f equal to minus 1, so it's plus 0.5 delta of f minus 1, which is f plus 1. So this is our spectrum, or the Fourier transform of x1 of t. So how did we get this? We got this just by looking at the spectrum and the basic knowledge of the delta function, which we discussed in an earlier video. But the mathematical process which would give us is the Fourier transform. So if we had taken x1 of t and applied Fourier transform to x1 of t, we would get x1 of f. Alright, I'll put a 1 here which is not needed. Okay, similarly, if we had to do it for x and plot its spectrum, so frequency on the x-axis and x2 of f, magnitude on the y-axis. Okay, these are magnitudes. So it had a component at 2 Hz and a component at minus 2 Hz. So that's minus 2 and 2, and both had an amplitude or magnitude of 0.5 and 0.5. So we would write this as x2 of f to be equal to 0.5, it's a delta function, delta of f minus 2, it is located at 2, plus 0.5 delta of f plus 2. So that's the mathematical notation or the spectrum of each of those signals, x1 of t and x2 of t. And again, just to elaborate this a bit further, x1 of t happens to be a cosine wave of frequency 1 Hz and amplitude 1 volt. So if we had to write the mathematical notation for x1 of t, it would simply be x1 of t is equal to cosine 2 pi ft. F is equal to 1, so it is cosine 2 pi t. Similarly, if we had to write for x2 of t, it will be x2 of t is equal to cosine 2 pi ft. F is 2 Hz, 2 pi into 2t, which we can simply write as cosine 4 pi t. So that means if we had taken cosine 4 pi t and applied Fourier transform to this, the answer would be what we have got here on top. So that would be 0.5 delta of f minus 2 plus 0.5 delta of 0.5 delta of f plus 2. Oh, it's not so clear, so let me just rewrite that. 0.5 delta of f plus 2. Now we have done this process intuitively by understanding what is the meaning of the spectrum, and first of all plotting the spectral diagrams, and then after plotting these spectral diagrams, by looking at those spectral diagrams, we have then written the expressions for the spectrum, which can also be done by computing the Fourier transform of the corresponding signals. Okay, now let's look at x3 of t and write the expression for the Fourier transform of x3 of t. So if you had the if you just redraw the spectrum of x3 of t, which is having a 1 Hz component and a 2 Hz component, so that's f on the x-axis and magnitude of x3 of f on the y-axis. So it had a component at 1 Hz and minus 1 Hz, so that's 1 and minus 1, and it also had a component at 2 Hz and minus 2 Hz, and all of them had an amplitude of 0.5. I'm just redrawing the spectral diagram which we had on the previous pages earlier. And if we had to write the expression for this magnitude spectrum, x3 of f is equal to, so it has a frequency component at 1 Hz and minus 1 Hz with a magnitude of 0.5. So this is basically a delta function at 1 Hz and delta function at 2 Hz. So we can combine the 1 Hz components together, so it is delta of f minus 1 plus delta of f plus 1, and both of them have an amplitude of 0.5. so that's the 1 Hz component, plus we have a delta at f equal to 2, so that's delta of f minus 2 plus delta of f plus 2, and again both of them have an amplitude 0.5. So that is the expression for the Fourier transform of x3 of t, so x3 of t, which is equal to cosine 2 pi t plus sine 4 pi t, right? And let me make a little correction on the previous side. This particular thing is not okay. This is the x2 of t we had earlier is sine, not cosine, but the magnitude spectrum remains the same, right? So I just need to write this as sine. So it's sine 4 pi t. Okay, right. So the magnitude spectrum tells us what is the frequency present in the signal and what is the magnitude of that particular frequency component, but it doesn't tell us what is whether that frequency component is a sine or a cosine or any other shifted version of the sine or cosine. But the convention that is followed is that the spectrum is represented in terms of the cosine wave. So we always represent it in terms of the cosine wave. So that means to complete the information we need the phase spectrum. In many practical scenarios where phase does not matter, we will use only the magnitude spectrum, but there are situations where the phase does matter, in which case we need information related to both magnitude and the phase. So we need both the phase magnitude and the phase spectrum. That is when we have the complete information. So magnitude spectrum, magnitude spectrum and phase spectrum. give complete information about the signal in the frequency domain. In the frequency domain, right? And how do we go from the time domain to the frequency domain? By performing what is called as the Fourier transform. All right, we'll discuss what the Fourier transform is and what are its properties and so on in a separate lecture. And we'll see you again soon with more details on spectrum and with, also with the information related to the phase spectrum in the next video. Thank you.